Good evening, everyone. Good evening, sir. So I welcome you all for the another session by Akshay Kumar, sir. Over to you, sir. We can start.
So, am I audible to you?
Yes, sir. Yes.
Okay, let me share my screen. So, last time, so is my screen visible to you?
Yes, yes,
Yes,
sir.
sir.
Okay. So, last time we stopped at a union of two subspaces. So we show that a union of two subspaces, say W1 and W2. So, a union of two subspaces forms a subspace if and only if either of them contained in the other one, right? So one can ask here, so suppose you have finitely many subspaces. So suppose you have W1, W2, Wn, finitely many subspaces. So are subspaces of a vector space V. So the question is when this union Wi equals to 1 to n, this forms a subspace. So do you know when this union will be a subspace? From audience, do you know when it will form a subspace?
So
Okay, so it
when
okay. Go ahead.
so when W1 is the subset of W2 and W2 is subset of W3 and sequentially it goes like Wn minus 1 is the subset of Wn.
So you are saying like this forms a chain like this: W1, W2, W3,
Yes, sir.
like this. Okay, this is one condition. If these subspaces will satisfy this condition, so it will form a subspace. Correct. Now, so if this satisfies, so this will form a subspace. Right. So what about the converse? So in two subspaces, we have if and only if, right? Now I'm asking, like, if you have this chain condition, then definitely this union will form a subspace. But what about the converse? This is correct. Now what about the converse? So let me take one example. Okay, without doing this also we can do this. Okay, suppose you take your W1 as x-axis, your W2 as your y-axis. So does W1 have any connection with W2? Are they related? No, W1 does not contain in W2, and the converse is also true. W2 doesn't contain in W1, right? Now, like similarly, if you choose W3 as your complete R2, right? So what is your W1 union W2 union W3? What is this union? This is the whole R2. It is still a subspace, right?
Yes, sir.
So the converse is not true. This one is not true. So what is the converse statement? So the converse statement is, suppose you have finitely many subspaces W1, W2, Wn, then union Wi forms a subspace if and only if for some j, so other subspaces will contain in Wj. So that means this for some j, so all Wi subset of Wj for all I means there exists a subspace that we are calling that subspace Wj, which contained all other subspaces. That's what that's what happening here also. Here W3 contained both W1 and W2, and that is also happening in two subspace case also. Correct? Okay. So now, so what can we do? Okay, so here we have finitely many. Okay, let's go to the infinitely many. So suppose you have Wn, right? So infinitely many, we can say this like Wi subset of Wj, like these kind of things. So question is, suppose you have infinitely subspaces. This is a subspaces of a vector space V, right? And like we, and when you can say that Wn union forms a subspace. So, like as of my knowledge, I don't know the condition of equivalent condition, but I can tell you, like if Wn's are not related to each other, like containment wise, then still this union may form a subspace. Like what I'm saying, it may happen that Wn is not subset of Wm for all n not equals to m. Right, Wn is not subset of Wm for any n not equals to m. Right, still that this union may form a subspace. Can you give me an example of this? Okay, think about R2. Right, this is 0 0. Right, now take all the lines. So L say R passing through this point of definitely, like I'm taking this lines passing through origin, different lines, right? So of course this is not a countable collection, but still if you take union of these lines, all these lines, so the union will give you R2. But if you take two different lines, L1 and L2, so L1 is not contained in L2 and L2 does not contain in L1, still This union is R2 and it forms a subspace. Definitely it is not a countable collection, but for infinite union we can take this example. So for infinite case we cannot say anything. Okay, now let's move to the spanning linear combination. So what is a linear combination? Why do we need linear combination? So if you observe that, suppose you have a vector space V. So of course non-zero vector space we are taking. So how many elements are there in V? So simple question is how many elements are there in V? Can you tell me how many?
Infinite.
Infinite, right? Why? So because if suppose you have any non-zero element x non-zero in V, and if you take any member from the field, so alpha x will be in the V. So for different alpha 1, alpha beta, again beta from the field F, beta x also in V. So in general alpha x, alpha belongs to the field F. It is a uh, subset of V, right? So every time we cannot take care of all the elements, right? Either because there are infinitely many members. So so we will figure out some smaller collection and we will work only on that collection. So the best way to do that is by taking linear combination, spanning set, and all these things to figure out a basis. So for that we need linear combination. So suppose what is a linear combination? Suppose you have a subset A of a vector space V and you have scalars from the field F. So linear combination of these vectors with respect to these scalars will be alpha 1 x1 plus alpha 2 x2. This is the linear combination of these vectors with respect to these scalars. So this is called linear combination of the given vectors with respect to given scalars. Okay, and what is the span of A? Span of A is you collect all possible linear combination linear combination from the members will come from A and scalars will come from F. Combination of members of A. This is called the span of A, right? So and it is easy to check that it will always form a subspace of V. So for till now we have taken only finite set. So what will happen if A is an infinite set? So if A is an infinite set, so first we take finitely many members of A, then take linear combination of those elements, and like this we will do. So span of A is, again we will take all possible linear combination of finitely many members of A. So this is the span of A, and in this case also it will form a subspace. Now, so suppose you have a like now the question is when span of A will be equals to A, when both the things will be equal. So as I said, a span of A is a subspace, always form a subspace. So definitely if span of A is equals to A, then this will imply A is a subspace. Correct. And you can prove that the converse is also true. So span of A is equals to span of is equals to A if and only if A is a subspace. Right. And the other question is what is span of A? What is this?
Span of A.
Yeah, because span of A, this one is a subspace. For subspace case, we have span of A equals to A. So this will be equals to span of A. Right. Now the question, another one you should ask is when, like, what is span of A union B? What is the relation between and the span of A union span of B? Okay, let me ask this. So as we said, span of A is always a subspace, right? Span of B is also a subspace. What about their union? Is it
May
always a
or
subspace?
may
I
not be.
Not
Yes.
necessary.
This is may not be, may not be. This is not necessarily a subspace, right? Now, what is the relation between this span of A union B and span A union span B? Are they equal?
No, sir.
No. So which one contained in which one? Which one?
Span of A union span of B is contained in span of A union B.
Okay, so you can prove this. This one is always containing this one. It's a very small exercise. Now, can you give me the example of the converse one?
In R2, if we take A equal to x-axis and B equal to y-axis.
Okay, that also work. So if you take A equals to x-axis and B equals to y-axis. So span of A will be your A only. Span of B will be B only. So A union B will be these two lines. Now if you take A union B, this will be this line and this line. Then you take span, then it will be whole R2. So it is a proper containment, right? So it may not be equal, right? Now, so okay. So suppose your sub vector space is okay. Let me uh, quickly do linear dependence and independent. So this is linearly dependent. So suppose you have a subset A, finite subset of a vector space V, right? So we say this set A. So we say this set A is linearly dependent if we can find scalars, say lambda1, lambda n, all are So I should write at least one of them is non-zero. All should not be zero, such that lambda1 x1 plus lambda2 x2 lambda n xn equals to 0. If you can find these kind of vectors, scalars, then you say this set is linearly dependent, right? And what is linearly independent?
If sir, lambda is if all lambda equal to zero, sir.
What happened?
So if all the scalars are equal to 0.
Okay, this is the definition of linearly independent. Okay, thank you. If say this is linearly independent, if you can find these vectors such that at least one of them is non-zero and this is 0. Uh, okay, this should be all. Okay, all are non-zero and this should be satisfied. Okay, this is correct. Okay, now we say a subset A of V is linearly dependent if A is not linearly independent, which means A is our finite set this, so we can find, so this is a subset of V, so we say this is linearly dependent if we can find scalars lambda1 lambda n from the field such that this linear combination is equals to 0 and at least one lambda I is non-zero. For linearly dependent, we have at least. For independent, it should be all. Correct? And if so as I said in the spanning set, so in this case it is called suppose span of A equals to, like suppose or W is a subspace and it is also equals to span of A for some set A of V, then it is called A is called spanning set of W. W. So if a set A is both linearly independent and spanning set, then it is called a basis for that vector space. Correct? So you can check that So suppose in R, so this singleton one is linearly independent and spanning set. So this is the basis for R. So say denote by this. And suppose you have an infinite set. For infinite set, suppose A is not a finite set. So how we will check this is linearly dependent or independent? So we say, so suppose A is an infinite set. Finite set we can check by linear combination. Here also we have taken finite linear combination. So and here also we have taken finite linear combination. So finite set we can check by linear combinations. But what about the infinite set? How to check infinite set? So a infinite set is said to be linearly independent if every finite subset of it is linearly independent, right? And conversely, if we say A is similarly is linearly dependent if at least one of its finite subsets is linearly dependent. If all finite subsets are linearly independent, then we call this set as linearly independent. If any one of them is linearly dependent, then we call this set as linearly dependent. Okay, and suppose V is a vector space and B is a spanning set and linearly independent, then it is called basis, and the cardinality of B is called the dimension of V. Cardinality of V is called dimension of V. So if B is less, if finite, then it is called finite dimensional. Otherwise, it called infinite dimensional. And suppose V is finite dimensional. So if B1 and B2 are any two bases for V, then cardinality of B1 will always be equals to cardinality of B2, and that will be equals to dimension of V. That's why we are calling it the dimension. The dimension. It is always unique. Okay. So in this case, what is the dimension of R? Of course, I am taking over R. What is the dimension of R?
1.
1. Correct. So what is the dimension of C over C?
2.
1.
C over
1.
C. Dimension of C over C is 1. Now what is the dimension of C over R?
2.
Then 2.
2.
So there is a result you like what this result says. So dimension of a vector space V over R is always equals to dimension of vector space V over C into 2. This is valid for all the provided V forms a vector space over C. That's why we are talking about dimension. If it doesn't form a vector space, we cannot talk about the dimension. Okay. So
Sir, can it be proved by ourselves? Uh,
yes, you can prove it.
okay, okay. And for this, there are no
we have already know the prerequisite for proving this result. Okay.
Okay.
Okay, sir. Then we will try.
You try it. It is not difficult.
Okay.
So
Okay.
okay. So okay. So let me take this example R2 over R. So you can check that this set. So suppose we take any linear combination. One zero plus beta 0, comma 1, and we take any linear combination and we put the linear combination equals to 0. The 0 element is this, right? Now what will happen? So this will give you alpha comma 0 plus 0 comma beta. This is equals to 0. So this is equals to alpha comma beta 0 0. So this alpha is equals to 0 and beta is also equals to 0. So this set is linearly independent because okay. So this set is linearly independent. Okay. So and you can prove that this is spanning set also. If you take any member x comma y, so you can write this as 1 comma 0 plus y into 0 comma 1. So this is x comma 0 plus 0 comma y. So this is x comma y. So this is spanning set also. So this is spanning set plus linearly independent. Right. So this is a basis for R2. And what is the cardinality of this set? 2. So the
2,
dimension of R2 is
2,
2. Similarly, if you take this example, so this is linearly independent and spanning set of spanning set for P and X. The polynomials, all polynomials degree less than equals to n. Now, how many members are there?
n plus 1.
n plus
N
1,
plus 1. So the dimension of P and X is n plus 1.
Plus 1.
To be precise, what is the dimension of P3X?
4,
3 plus 1, 4. Right. Now, similarly, if you can check that, so the EIJ, suppose this is M cross N matrix, right? So all entries are 0 and the ij position we have 1 only. Okay, at the ijth position we have 1, other entries are 0. Okay, and if you, it's not tough to check that I varies from M and J varies from 1 to N. So this set is linearly independent and spanning set for M, M cross N, all the matrices of order M cross N. Now what is the cardinality of this set?
M into n.
Amen.
Yeah. So the cardinality of this set is M into N. So dimension of this space is M into N. And in particular, what is the dimension of n cross n matrices, n cross n matrices is n square. Right. Now suppose what is the suppose you have two subspaces W1 and W2. Right. Now if you add them, what is the addition? Addition is simply W1 plus W2, where W1 belongs to this capital W1 and W2 belongs to this capital W2. So you can check that this addition will always form a subspace. Right. And if W1 intersection W2 is 0, then we write V as W1 direct sum W2. Right. So in this, if you have this kind of situation, so dimension of W2 in this situation, dimension of W2 is called the codimension of W1 in V. So dimension of W, this dimension called the codimension of W1. Okay. So yesterday I asked, like last time I asked one question. So suppose you have V equals to W1 direct sum W2, and you also have V equals to W1 direct sum W3. So what you can say about W2 and W3? What is the relation?
Sir, they will
W1
have
is
same
equal to
dimension.
W3.
W1,
W2 is equal to W3, I guess he is saying.
okay, suppose you take this example. So suppose your V is your R2. Okay, so take your W1 as your x-axis, W2 is your y-axis. So is V equals to W1 direct sum W2?
Yes, sir.
Okay. Now if you take W3 is y equals to x line, this line. So you can check that V is equals to W1 direct sum W3, but W2 and W3 doesn't contain W2 and W2 also doesn't contain W3. So in general they may not have any relation. So they may not have any relation.
Sir, we can say that their dimension will be same.
Yeah, dimension will be same.
Yes, sir.
Dimension will definitely same, because what the theorem is there. So one theorem is there. So dimension of W1 plus W2. So if you are talking about dimension, like if you are okay, so this is dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So we are doing this only for finite dimensional. This is for finite dimensional only. So if V equals to W1 direct sum W2 and W1 direct sum W3, so by this you can prove that this one is V, dimension of V. In both the cases it is same. W1 is same in both the cases. This is 0 in both the cases. So W2, so you can find it, it will be equals to the dimension of V minus the dimension of W1, and it will be same in both the cases. Okay,
Yes, sir.
so let me ask one more question here. Suppose you have one subspace W1, okay, and you have one more subspace W2. So when a dimension of W1 intersection W2 will be equals to dimension of W1 union, okay, let me put only W1. So when it will happen?
If W1 is contained in W2.
W1 contain in
W2.
is it?
Yes, sir.
Think about it. Maybe the reverse one. So it will happen. So now suppose
If W2 is contained in W1.
okay. So suppose W2 is subset of course I'm not talking about okay. So if W2 is subset of W1, right? So what is this intersection? Intersection always form a subspace, right? So it is a subspace. So W2 is subset of W1. Then what is W1 intersection W2?
W2.
So this is W2, right? So this is will be now if so this is not our case, right? Now if W1 is subset of W2, so from this we are not getting our this condition. So if W1 is subset of W2, so what is W1 intersection W2? This is
W1.
W1, right? So both the subspaces are equal, so their dimension will be equal, right? So this is our condition. W1 should be subset of W2. Okay. Now what should we ask? Like what is the okay? So if this condition holds, then this will happen, right? We have just checked. Now what can we say about the converse? Of course, if you take W1 equals to 0, right, then both are equal, right? Like don't take this case, 0 case we are not taking. So W1 intersection W2, we are not taking this case.
Sir, I think converse is also true.
Yeah. So let's go step by step. So we are saying, so first notice that, so W1 intersection W2 is always a subset of W1, isn't it?
Yes, sir.
Okay. So dimension of W1 intersection W2 will always be less than equals to dimension of W1.
Yes, sir.
Yes, sir.
Correct? Okay. So what we are saying, so W2 subset of, we need to check this one. Okay. Mhm. Okay. So I think this may not be happen always. No, this is not always true. This is not always true. So we can find the counter examples also. Just take, so what we need, dimension of this one equal. Okay, and W1 should not be subset of W2. Okay, that we can find. Simply take this W2 equals to, okay, let me write here. This is not always true. The converse is not always true. This converse is not always true. The example is, you simply take W1 is your x-axis, right? And okay, we need this dimension. So this part, okay, how to prove this? Okay, when this one is done, the converse is, the dimension is equal. Okay, so we want to prove this W1 is subset of W2. Okay, you can prove like this. So suppose W1 is not a subset of W2. So if this is not a subset of W2, right? So there will exist a member.
Element in W2 which is does not contain in W1.
Yeah, that will contain a member W1, right? So which is linearly independent from W2, right? If it is linearly dependent to W2, W2 is a subspace, then X has to be a member of W2, correct? Now, since we are taking X is not a member of W2, so we can take that X belongs to W1 and that is linearly independent from the W2, correct? Now, so since this it belongs to W1, right, and this does not belongs to W2, so the dimension of, so X does not belongs to this W1 intersection W2 because X does linearly independent to W2, correct? Now, so like this member is linearly independent to W1 intersection W2 because it is linearly independent to W2, so it has to be linearly independent to W1 intersection W2, so it will be linearly independent to W1 intersection W2. So we have a member which is linearly independent to W1 intersection W2, which is also a member of W1. So what it says, so dimension of W1 has to be greater than dimension of W1 intersection W2, which is not our case. We are assuming that dimension are equal. So the converse is also true, right?
Yes, sir, got it.
Okay. So I think we can solve some questions now. Okay. So this is your last year questions. 2023 15th questions. So in exam they asked that suppose you have two non-empty subsets S and T. So S and T are two subsets of R2. W is a non-zero proper subspace. So consider the statements. So first statement is if you take span of S, it is R square, right? So span of if you take span of S intersection W, so it will be W. So it is true or false? You take S intersection W and that then take span of that. So it will it be equals to W? For example, you simply take this R square, right? W as your x-axis, right? And you take these 2 points, 1 comma 0. So okay, I should take, you take this point 0 comma 1 and you take this point 1 comma 1, right? So B is 0 comma 1 and 1 comma 1. So what is the span of B? Span of B is R square,
R2
right? What is B intersection W?
empty set.
This is empty set. And we always assume that span of empty set is always singleton 0. We assume that this is always true, right? So this statement is false, right? And we just check that this statement is also false, right? We have seen that span of S union T may not be equals to span of S union span of T. Correct?
Yes, sir.
Yes,
Yes,
sir.
sir.
Sir, please can you explain the statement on why it is false? I am
Your
clear about the
voice is
statement too.
your voice is not coming clearly. Can you repeat it again?
Yes, am I audible now properly?
Now tell me.
Yes, can you explain please on why option one is false and particularly those example you have given here?
Okay, so first example. So suppose you take your vector space as your V as R square,
Yeah.
right? And if you
Yes, sir.
take your set your S, take your S as 1 comma 0, no, 0 comma 1 and 1 comma 1. So this set is linearly independent,
Yes, sir.
right? And span of S is
To
R square,
R
sir.
square.
right? So span of S is R square. The first condition is satisfied, right? Now
Yes,
what is S intersection W? Here W is x-axis.
yes. Um, 5.
Yeah, so empty set, right? So what is, we always assume that span of empty set is
Singleton set 0. Second bracket.
0,
Yes, sir.
right? So
Yes, sir.
but this is not equals to W,
Yes.
right? So the first
Mm.
statement.
Yes, sir. Got it.
Okay, so both statements are in general false.
Yes, sir.
Okay,
Yes, sir.
okay. So the next question is they asked in 2024, question number 13. So suppose V is a non-zero subspace of complex vector space M7C. So what is M7C? The collection of all 7 cross 7 matrices. Right? So, and your V is a subspace. Okay. So this is your vector space. V is a subspace. V is a subspace of this vector space. So subspace is such that all matrices, all non-zero matrices of V V is invertible, are invertible. Right? So what is the dimension of V? Okay, so it is not straightforward actually. So suppose always the entity matrix is always invertible, right?
Yes, sir.
Okay, so the result is if you take span of I, it always equals to this V, not the whole vector space, this V, the space of all uh, the space in which all non-zero matrices are invertible. So how to prove this? So let me prove this. So suppose you take any any B from this space V, right? And if you take any now if you take this polynomial or this polynomial G lambda equals to so B minus or plus lambda I. Now this is a matrix, right? This is a matrix, right? Are you getting me? This is a matrix,
Yeah.
right? Now if I take determinant of this is a polynomial, right?
Yes, sir.
This is a polynomial. Now we are in the complex field, right? So what
Yeah.
do you know fundamental theorem of algebra?
Yes. Every polynomial is of degree n in the field complex. They are
That
at
must n roots.
uh,
Has exactly n roots,
yes.
Yes,
but that is not valid for real numbers, right? For that we
Okay.
need complex field, right? That's why we need complex field here. So we will have at least one root. Even we will have exactly roots equal to the degree of that polynomial, but still we will have at least one root. Suppose that root is lambda naught, right? So this G lambda naught is equals to 0 for some lambda naught, right? So can this lambda naught be 0?
No, sir.
Why?
Because if we put then determinant of B plus 0,
Yeah.
this is not zero because B is invertible.
So of course we are taking non-zero B. So if we put lambda equals to 0 here, lambda naught equals to 0, so it will be determinant of B plus 0 I. So it will be equals to determinant of B,
B.
right? So B is belongs to V and B is not invert. B is invertible,
Yes, sir.
right? So lambda naught cannot be 0, right? So we have some lambda naught not equals to 0 for which this is this G lambda naught is 0, right? Now what is this? Determinant of B plus lambda naught I, right?
Yes.
So what is this? B plus lambda naught I is also a part of V,
Yes.
Yes, sir.
and the determinant of this is 0, right? So, and what
Yes,
is the
sir.
property of V? The property of V is every non-zero matrix is invertible, right? So every non-zero matrix is invertible, right? So this is not invertible because determinant is 0. So this has to be 0 only.
Yes, sir.
So B has to be equals to minus lambda naught I. So B belongs to span of I, correct?
Yes, sir.
So we take any non-zero member and that belongs to span of I. So what is V? Span of
I.
I, right?
Yes, sir.
So and what is the dimension of this?
So 7.
7?
No, sir. 1.
1. Only
It's,
one
mm,
one member. This is one
oh,
member and
yes,
we are
yes.
taking
Okay, okay,
spanning
okay.
of this. Span of this. So dimension is always 1.
1.
Right? Okay. So let's move to the next one. Okay. So here P11x is the space of all polynomials, real coefficients. So our field is real. Okay. And the dimension is at most 11. Together, okay, together with the zero polynomial. And we have two set, E and F. So what is E? E have 11 members such that S not S1 and S11. So it has 12 members. Okay. So what is the dimension of P11? 12. Right. So what? How many members are there? 12. Right. And again, F is a set. And how many members are there? 12.
12.
Right. So both sets have equal members and the numbers are 12. Okay. Now which one is like, and they also satisfy these conditions, right? Then which one of the following is true? Okay. So let's see the second set first. This F. So if we take, so this set is 1 x x square x to the power 11 is a basis for P11x, right?
Yes, sir.
The only problem is they may not satisfy this condition, right?
Right.
Now, for first member is um, like this first member is satisfying this condition, right? Because no x is there, so it is always equals to 1. So first member is satisfying this condition, right? Now, what about the second member? Although x is not satisfying the condition, so can we put x minus 3 here, right? Now, what about the third one? Third one is so x square. So if we put x equals to 4, what is x square? 16, right? So it is not equals to 1. So 16 minus 15, it is 1. Now what is 4 cube?
64.
60?
64.
64. So what if I subtract with the 63? Like this, x to the power 11 minus some number will be there, right? Like this. So this set is again linearly independent and spanning set. Now come to the, so this set F can be linearly independent basis and spanning set also. Now the first question is, the first option is, so any such F is not necessarily linearly dependent. Okay, so we should go for the is necessarily such statement. So any such F is necessarily linearly dependent. We have just check one set which satisfy all the properties of F, but that is linearly independent. What this statement saying? Any such F is necessarily linearly dependent. So this is not true, right? So this statement is false. F may be linearly independent. So F can, so the question is F always linearly independent? So what do you say? Is F always linearly independent?
No, sir.
No, of course not. You just take F as 1, 1, 1, 1 like this. Okay. Like this kind of set if you can take. If members are repeating. Or like better you can take like F as, you can take your F as, if you don't want to repeat the members, you just take 1 x minus 3. Okay, this is not satisfying that property. X minus 3, so 2x minus 6 like this. So these members are not linearly independent. So this F set may be linearly independent, may be linearly dependent. So it's totally depends on the members, how their members are. For F we cannot say anything. Okay.
Yes, sir.
So the remaining, this statement says any such F is necessarily linearly dependent. Again, we cannot say anything about this. It may be linearly dependent, it may be linearly independent. Okay, so these two statements are correct. So F is not necessarily dependent. Okay, F is not necessarily dependent. Okay, these two are correct. This part is correct. This part is correct. Now what about E? So S3, S1, S11, 3 equals to 0. So if you notice that, so how many members are there in E?
12.
12.
12. Okay, so there is a result. So if dimension of a vector space is n, then and B is a basis for V if and only if cardinality of B is equals to n and B is linearly independent. Okay, this is if and only if B is cardinality of B is n and B is a spanning set. So these are if and only if statements. Now, so suppose V is E is either linearly independent or a spanning set. So it will be a basis for, so suppose span of E, suppose E is linearly independent. So if E is linearly independent, So E has to be a basis because the cardinality of E is 12, right? And the dimension of the vector space is also 12. And if E is linearly independent, so by this result, so E has to be a basis, right? So if it is a basis, then span of E will be V, right?
Yes, sir.
Now, if you take so here what the members of E are satisfying this condition, right? So what you can do with this condition? So if you take x minus 2, that you take any polynomial in which 3 is not a root of that polynomial. So I am taking x minus 2. If you can take x minus 4, x minus 5, x square minus something like that you can take. So x minus 2 belongs to P11R clearly, right? Since this is a spanning set for V, so x minus 2 will be a linear combination of members of E. Yes, right. Equal 1, 0 to 11, right? So for all these members, 3 is a root, right? So 3 is a root of all these polynomials, right? So what can you say about this? 3 has to be a root of x minus 2 also, but that is not true. So the problem is this cannot be a spanning set. So this problem is this cannot be linearly independent. So it has to be linearly dependent. So any such E necessarily linearly dependent. It has to be linearly dependent. Otherwise, it will span the whole space, and 3 will be a root of x minus 2. But that is not true. So the B option is correct. Okay. So one more question is there. Okay, P12x with the real vector space of polynomials in variable x with the real coefficients with the 0 polynomials. Now the space V is your polynomials which satisfy this condition, that is called even polynomials, even functions, right? And this is also a root of this, right? Now, so what we can say here is, okay, so what is the dimension of V? So what is the dimension of V? Okay, so what is the general form of even polynomial? So actually the even polynomials look like a0 plus a1 x square plus a2 x to the power 4 plus a3 x to the power 6 plus up to 12. So like this, a4 6 maybe 6 8 a4 x to the power 8 a5 x to the power 10 a6 x to the power 12. This is the general form of even polynomials of degree at most 12, right? So you can see that 1 2 3 4 5 6 and this one. So what is the spanning set for this one? This one x square
X
x4 x6 x8 x10 x12 is the spanning set for even polynomials. Right. So how many members are there? 3, 3, 6, and 1, 7.
7.
Right. But this is a span of for even polynomials. Right. One more condition is also given, that is f 2020 f of 2024 equals to 0. Right.
This constant will reduce the dimension of
So
one by
similarly, you
1.
can see that this one. So if you replace this point by 2024, x4, x4, x6, x12. So this is also a spanning set, right? So the polynomial should satisfy this condition. Okay, don't go for this. Okay, so what can you say about this? We can change this part, right? How? So x square minus some number, x e to the power 4 minus some number. We want like x square minus 2024 square. So it will be 0. Similarly, x to the power 4 minus 2024 to the power 4. X to the power 12 minus 2024 to the power 12. So we can manage all the remaining terms except one. We cannot manage one. So we left with how many terms? How many linearly independent elements are there if we apply this condition?
5.
We have deleted this one only.
The 6.
So 1, 2, like 1, 2, 3, 4, 5, 6. So dimension is 6. Okay. So similarly, you can solve this one. So what is the question? Suppose P7x with the vector space of polynomials. Now what we have given, so the form of SR is for S not x is 1, right? And what is S1x? We put R equals to 1. So this is x into x minus 1. Okay, R minus 1. Okay, this is x only. So this is x. So what is S2x? X into x minus 1. What is S3? X. X into x minus 1, x minus 2. Like this. We have S, all these S. Right. Now it is given that, consider the fact that this B, the collection of all these polynomials, is a basis for this set, vector space P7x. Right. So, and we have given that x to the power 5 is equals to summation k equals to 0 to 7 alpha 5k as kx, right? And we want to calculate the value of alpha 5 2, right? Now if we put k equals to 0, right? So you can observe that, so 0 is, okay, it is not k. If we put x equals to 0, right? So you can observe that x is a root of all the polynomials, right? Except this as not x. So if we put x equals to 0, so left hand side will be 0, right? So only remaining term is alpha 5 0, right? Into as 0 0 plus other terms will be 0. So what is the value of s 0 0? 1. So what is the value of alpha 5 comma 0? It is 0. Right? Similarly, you can check that for x equals to 1, x equals to 1 is a root for all the polynomials s2, s3, s4 like that. Now, if you put x equals to 1 both side, what you will get here? 1 to the power 5. So 1 equals to alpha 5 1, and as alpha naught as naught 1 plus alpha 5 k equals to 1 1 as 1 1 plus for s2 and greater polynomials, 1 is a root of all the polynomials, so it will be 0 plus 0. Right, this part is also 0 because alpha 5 0 is also 0. Right, so the remaining is 1 equals to, so what is s1 of 1? This is also 1 from here. So alpha 5 1 equals to 1. Right, now similarly, if you put x equals to 2, then from s3x, s3 2 will be root of all the polynomials from here. Right, now if you put s equals to 2, what will happen? So it will be 2 to the power 5, left hand side, equals to alpha 5 0 s 0 of 2, right, plus alpha 5 1 of 2, right, as 1 of 2 plus alpha 5 of 2 as 2 of 2. What is 2 to the power 5? 2 to the power 5, this part is 0 plus what is the value of alpha 5 1? 1 into what is the value of s1 2? 2 plus alpha 5 2. What is the value of s2 of 2? It is 2. So from here you can find the value of alpha 5 2. So with this, I think we should stop here. If you have any questions, you can ask. Okay, so maybe I made some mistakes, so let me correct it. So during the definition of linearly independent and dependent, so I should write once again. So a set A, that is suppose finitely many. So this is set A in vector space. So says it's said to be linearly independent if you take any linear combination. You take any linear combination, and if this combination is equals to 0, then this will imply all alpha I should be 0. This is the definition of linearly independent. If this combination equals to 0, then all alpha I has to be 0. And so if you write linearly dependent, so a set is said to be linearly dependent if you can find alpha 1 alpha n, at least one is non-zero, such that alpha 1 x1, this linear combination, is equals to 0. This is linearly dependent, this is linearly independent. Right, maybe I made some mistake during defining those things, so I'm correcting these things. Okay, if you have any questions, please feel free to ask.
Yes, sir. In case of linear dependence, you have choose any linear combination, and that way that if this is equal to 0, and for there exists at least one alpha which is not equal to 0, then this set is linearly dependent. Okay.
So this is the definition.
Yeah.
The correct definition, linearly independent dependent.
Yes, sir. Here, choosing any linear combination, and this definition also follow in case of whether A is finite or infinite. In both cases,
So,
this definition will hold.
so actually, that this concept is only for a finite set, right? So if you have infinite set, so we say A is linearly independent if every finite subset of A is linearly independent. Then it is called linearly independent. This is only for finite subset. Right? If you
Ye-
want to go for infinite subset, then you take every finite subset of that set. If that is linearly independent, then A is linearly independent.
Okay, sir.
If any subset, if you can find a particular subsets, you said F naught of A, this is linearly dependent, then this is linearly dependent. This is uh, this is for all finite subset, and this is if you find a subset. This is, means any subset. This is for all subset, right? This is not all subset. Like suppose A is your if you take anything like 1 x square like this, right? F is your any subset, but F not can be your is your precise set. I'm saying, right?
Yes.
If you take a precise subset and you are you can show that this is linearly that is linearly independent, then you can say that the whole set is linearly dependent. Here
Uh,
I was giving example for particular set, not for linearly dependent. This is particular set
uh,
I'm saying.
any superset of linearly dependent subset is also linearly dependent. Uh, uh, and
Superset of a linearly dependent set is linearly dependent, of course.
mm, yes, yes.
But subset of a linearly dependent set may not be linearly dependent. The simplest example is you take any vector space V, non-zero vector space, right? Vector space itself always linearly dependent, right? The vector space itself is always linearly dependent, but you can always find a basis for that vector space. Every vector space has a basis, and basis is always linearly independent. So from here you can find a linearly dependent subset of a linearly dependent may not be linearly dependent. It may be linearly independent. Superset of a linearly dependent is always linearly dependent.
Yes.
Superset of linearly independent may not be
Be
linearly
linearly
independent.
independent. Yes.
Okay, I can pose one question. I remember one question. So, do you know this space C naught sequence all real sequences which converges to 0? Have you seen this space? All real sequences which converges to 0. And if you take C, all real sequences which are convergent only. We are not saying where it is converging, but that is convergent, that we know. So you can prove that this is a vector space and this is a subspace. So C naught is a subspace, right? The question is, we have seen what is the codimension. So the question is, what is the codimension of
C naught.
C naught in C. If you
Okay.
know little bit real analysis, then you can figure out it.
Okay, sir. Thank you, sir, for giving question.
Okay, any other questions?
I think, sir, if I joined 5 minutes late, sir, have you put any homework at the right from your beginning of session?
Today?
Today, only today.
No, I did not.
Okay. Okay. And sir, one thing, in those question 24, one of the question here, C7, and you have proved, yeah, just
This one?
uh, no, this one, not dimension only. Yes, this one. Yes.
Okay.
Here, here I have a question. I am understood this what is the process you have done here, but I have one question, sir. Uh, it is the claim that the span of I is equal to V. It was first claim, but
Yeah.
huh, how can think this intuitively at first in the examination hall, that if I intuitively think that this is the span of V, then logic are uh, always then easy, but at first it seems
See, this is
to quite.
this is a genuine question, but see, this one is a standard question. You can see
I
this question in many books. This is a standard question. Like in this question, this is not a standard question. They can change. They can edit these things like these S3, S4, something like. They can do anything with these things, right?
Oh,
In this case, you have to think like what we can do here, right?
yes,
But this is a standard questions. Like there are the particular subspaces. Like what is the dimension of symmetric matrices? What is the dimension of skew symmetric
yes,
matrices? These things are very like popular questions. So in like you have to remember these things.
and
Of course,
I
in
think that here main invertible, in case of invertible, we should, uh, if you have not read the rank of matrices, you have not defined in your class, but I think if I think that it has full rank, it is invertible. So anyhow, it has some multiple of identity matrix. Okay, that is why if
how will you relate this thing with the rank of a matrix? Here, your space is all like space is consisting of matrices. It is not a single matrix.
okay, sir. Okay, sir. Thank you.
Okay.
Okay, so I think it's now if there are any more doubts that can be taken up in the next session.
Sure, ma'am.
Yeah. So thank you so much, sir. So we'll meet in the next session. Thank you, participants.
Thank you.